The compressor is the heart of a refrigeration system. It compresses low-temperature and low-pressure refrigerant vapor into a much smaller volume. As the refrigerant is compressed into a smaller volume, its temperature and pressure increase. The pressure is increased from a low-pressure level at the compressor's inlet to a high-pressure level at the compressor's outlet. Compressors are driven by an electric motor, which may be mounted outside the compressor unit or inside its housing. Compressors that are driven by an external motor are called open-drive compressors, and compressors that include an integrated drive motor in a sealed unit are called hermetic compressors. An open-drive or external drive compressor is driven by a mechanical power source that is separate from the compressor unit. Most often, this is an electric motor. There are two different ways of joining a motor to an open-drive compressor: direct drive and belt-driven. A direct drive compressor is driven by a coupling connecting directly to the compressor shaft. The compressor turns at the same speed as the motor. On a belt-driven compressor, a belt connects a pulley on the drive motor to a pulley on the compressor's shaft. In a hermetic compressor, the motor is sealed inside the same housing as the compressor. The motor is directly connected to the compressor, often through a shared shaft. Some are enclosed in a bolted assembly. These types of compressors are often called semi-hermetic, field serviceable, or accessible. Fully hermetic compressors are sealed in a welded casing.
In addition to the open drive and hermetic classifications already presented, compressors can be further classified based on their method of compression. There are 5 basic types of compressors in use in the refrigeration and air conditioning industry: reciprocating, rotary, scroll, screw, centrifugal. A reciprocating compressor is a compressor that functions by changing the rotational movement of a crankshaft into the reciprocating motion of the pistons within cylinders. These compressors are classified in a number of ways: by cylinder arrangement, by number of cylinders, by type of crankshaft, by construction, open drive, semi-hermetic, or hermetic. Like an automobile engine, a reciprocating compressor has a crankshaft, connecting rods, pistons, cylinders, and intake and exhaust valves. Reciprocating compressors are usually driven by an electric motor. The motor's rotary motion is changed to reciprocating motion, back and forth action in a straight line, through the action of a crankshaft and connecting rods. The reciprocating motion moves pistons up and down in cylinders to draw in and compress the refrigerant. A rotary compressor is a compressor in which vapor compression takes place in spaces between the cylinder wall and sides of an off-center rotor that spins inside the cylinder. A check valve is usually placed in the discharge. It prevents backflow of refrigerant during the off cycle. A rotating vane rotary compressor uses an off-center rotor to turn blades that create pockets between the rotor and cylinder wall. The vanes are spring-loaded, so they can adjust position and continually push out against the cylinder walls as the shaft rotates. The blade on a stationary blade rotary compressor is mounted in the housing assembly rather than on the shaft. The blade in this type of compressor is spring-loaded and presses against the rotor as it rotates. An eccentric shaft turns a rotor within a cylinder. This rotor continuously rolls against the outer wall of the cylinder. As the rotor spins, the blade traps an amount of vapor between the cylinder and rotor. The vapor is compressed into an increasingly smaller space as the rotor turns. Ultimately, the pressure causes the exhaust valve to open, forcing vapor through the exhaust port. The compression of one quantity of vapor occurs simultaneously with another quantity of vapor filling the cylinder during the intake stroke. A scroll compressor generates vapor compression within the confines of a stationary scroll and a moving scroll. The primary components responsible for compression are these two interlocking scrolls. One of the scrolls is secured to the housing and stays in place, whereas the orbiting scroll rotates in an eccentric trajectory around the center of the fixed scroll.
Vapor enters the outer pockets between the scrolls. The full amount of vapor fills the inlet space for the first set of pockets. As the moving scroll orbits, it seals the pockets. The pockets get progressively smaller and pressure increases. The lead pockets are forced to the center of the scrolls, where the compressed vapor escapes through the discharge port. Note that new vapor pockets form continuously during the cycle. Screw compressors use a pair of special helical rotors to compress refrigerant vapor. The rotors trap and compress the refrigerant vapor as they revolve in an accurately machined compressor cylinder. In a screw compressor, the revolving rotors compress the refrigerant vapor. A. Interlobe spaces being filled. B. Beginning of compression. C. Full compression of trapped vapor. D. Compressed vapor discharge from interlobe spaces. A centrifugal compressor is a compressor consisting of a rotor-operated impeller with radial blades inside a volute casing. As the rotor spins, it flings refrigerant vapor outward, where it compresses against the volute casing. The force that throws the vapor outward is called centrifugal force. Because the compressors rely on centrifugal force to compress the refrigerant, their efficiency increases with speed. In this type of compressor, the vapor is fed into a casing near the center of the compressor. The impeller is a disc with radial blades that spins rapidly in this casing. The vapor is flung outward in the casing, piling on top of the vapor ahead of it, causing slight compression. These compressors are designed to operate at high speeds. The pressure gained is small, so multiple impellers may be used in series. This creates greater pressure difference and pumps a sufficient volume of vapor. In summary, the compressor is often referred to as the heart of the refrigeration system. Just as a human heart pumps blood throughout the body to sustain life, the compressor pumps refrigerant through the system to sustain the cooling cycle. Without the compressor, the entire process of artificial cooling would be impossible as it creates the necessary temperature difference, drives the circulation of the refrigerant, and maintains the system's pressure differential.